A certain radioactive isotope is a byproduct of some nuclear reactors. Due to an explosion, a nuclear reactor experiences a massive leak of its radioactive isotope. Fortunately, the isotope has a very short half-life of 6 days. Estimate the percentage of the original amount of the isotope released by the explosion that remains 5 days after the explosion. So we're assuming here that we're dealing with another exponential growth and decay model. So we're following this model, A equals A naught e to the kt, where A naught is the initial amount, K is the growth or decay rate, and in this example, our radioactive isotope has a half-life of 6 days, meaning that it is decaying, and so that means our example will have a decay rate, and the value of K will end up being negative once we calculate it. Then we have T, which stands for time, and the value of A is the amount after time. So with this piece of information here, given that the half-life is 6 days, is enough information that I'm going to be able to calculate the decay rate for this model, for this radioactive isotope. So what that tells me is that if there is a half-life of 6 days, that tells me that the amount of that isotope will become half of whatever it started with, hence the word half-life, half of what it started with after 6 days. So our amount after time will be half of our starting amount, our initial amount, at a time of 6 days. So this is going to give me values to substitute into the exponential model. We have A equals A naught e to the kt. In for A, I'm going to substitute 1/2 A naught, because we're going to go to half of what we started with. We'll leave that A naught alone, and we're going to substitute in for time the 6 days, which is the half-life. So we're going to be able to solve this exponential equation by isolating the exponential portion. We would divide both sides by A naught. That cancels out the A naught on both sides. So I have 1/2 equals e to the 6k. I'm going to solve this exponential equations. We have 3 methods that we typically use. Relating the bases, which we can't do in this example. Converting to a log or taking the log of both sides. I'm going to take the log of both sides. I do the natural log on the left and the natural log on the right. Now that we've introduced the logs, I can use the power rule for logarithms. And the power rule for logarithms allows you to take this exponent and make it the coefficient of the log. We have 6k natural log of e equals natural log of 1/2. Natural log of e is 1, so that gives me 6k equals natural log of 1/2. And then I can divide both sides by 6. So we have k equals natural log of 1/2 over 6. I'm going to type this into my calculator. Let me clear these buttons so you can follow along on which ones I pushed. So we have natural log of 1/2 over 6. And this is going to be my decay rate. You can see that decay rate came out to be negative. So we're going to round to 3 decimal places. That would be negative 0.116. And even though I calculated that decay rate to be a decimal, I'm going to use the exact value of natural log of 1/2 over 6 in my calculation, because you don't want to round too early in these problems. It can cause rounding error. So now we're going to take a look at the second part of the problem. It says estimate the percentage of the original amount of that isotope released by the explosion that remains 5 days after the explosion. So we're now given a time of 5 days, and we want to estimate the percentage of the original amount. Remember, we were never given the original amount. We want to find the percentage of the original amount that remains after 5 days. So we have a model, and that model is A equals A naught, E, and the K that we just figured out, natural log of 1/2 over 6, T. We're going to substitute in that time of 5 days, and then we're going to do a calculation of this portion. That portion will be the percentage of the original amount that's remaining. So in our model, we're substituting in for T. We're substituting that value of 5. I like to write the 5 in the front because it's easier to type in the calculator. So we would have 5 natural log of 1/2 over 6 is what we're typing into the calculator. So I'm going to type E to the 5 natural log of 1/2 over 6. So that gives me, I didn't memorize that, 0.56. Okay, so we've got 0.56, which we'll round to those 2 decimal places. And I know I've got a long chain here, but on the left, I've got this A, and on the right, I have 0.56 times A naught. A equals 0.56 A naught. That's A equals 56% of A naught. So the amount that we have after 5 days is 56% of the initial amount. So the amount after 5 days is 56% of the initial amount. And that is what the question asked for. the percentage of the original amount that is remaining after 5 days. A toy rocket is shot vertically into the air from a 7-foot tall launching pad with an initial velocity of 40 meters per second. Suppose that the height of the rocket in feet, t seconds after being launched, can be modeled by the function h of t equals negative 16t squared plus v naught, that v naught stands for initial velocity, times time, plus h naught, that stands for initial height, where v naught is the initial velocity of the rocket and h naught is the initial height of the rocket. How long will it take for the rocket to reach its maximum height, and what is its maximum height? So we have this function, h of t equals negative 16t squared plus v naught t plus h naught. V naught is the initial velocity, and it's given here that the initial velocity is 40 meters per second. So we can substitute in for V naught of 40. And then since we are launching from a 7-foot tall launching pad, we know the initial height of this toy rocket. So we can modify this function to be negative 16t squared plus 40t plus 7. So this function models the height of the rocket. So it's the height of the rocket in feet, t seconds after it is launched. So that means that if we choose a value of time to substitute into this function, we're going to get the height of that toy rocket at that moment in time. The question here says, how long will it take for the rocket to reach its maximum height? And what is that maximum height? So when I look at this equation, what I notice is that it is a quadratic equation because of the squared. And the graph of a quadratic is a parabola. And this one happens to be a down-facing parabola because of the negative leading coefficient. So if I'm looking for the maximum height, that will occur at this point here, which is called the vertex of the parabola. So we're going to be able to find the maximum height at the vertex. So as I said, the maximum height will occur at the vertex. Now we have a formula for calculating the vertex of the parabola. And the vertex is an ordered pair, HK. And the formula for the x-coordinate of the vertex, h, is negative b over 2a. We can find the y-coordinate of that vertex by substituting the x-coordinate into the function. So we would substitute into our height function negative b over 2a. So we'll find the vertex for this example. So for this example, our value of A is negative 16, B is 40, and C is 7. So the x-coordinate of the vertex is negative 40 over 2 times negative 16. That's a negative 40 over negative 32, which is 1.25. Then we can find the y-coordinate of the vertex by substituting that 1.25 into the function. So we're doing the height at 1.25 seconds, and we'll use our calculator to do this. Let me write it out first. We're doing negative 16 times 1.25 squared plus 40 times 1.25 plus 7. And this is what we'll type into our calculator. We have negative 16 times 1.25 squared plus 40 times 1.25 plus 7, and we have 32. So this toy rocket reaches a maximum height of 32 feet at a time of 1.25 seconds. We have a max height of 32 feet at 1.25 seconds. Thank you for checking out my videos. Have a great day.